Hi everyone, it's time for your favorite videos, Chemistry with Miss Nichols. Woohoo! So today we're going to be learning about heating and cooling curves. And so a heating curve, I'm just going to zoom in on this one here, is a graph that represents how the temperature changes as you add in heat, which also we know is going to take time. So your x-axis can be measured by either the amount of heat added, or it can be measured that the time as it's, occurring. You'll sometimes see it as both ways. And then on our y-axis, we have temperature measured in degrees Celsius. Now, with our temperature, our heating curve is a heating curve of water. So there are two really important temperatures when it comes to water. The first one is 0 degrees Celsius, which let's see if I can make that a little more readable for us. 0 degrees Celsius, which is the temperature that water will begin to melt or freeze, depending on whether or not you're heating up or cooling down. And then 100 degrees Celsius, which is the temperature that it begins to boil or condense, depending on, again, whether or not you're heating up or cooling down. Now, because this is a heating curve, that means we're starting here at -5 degrees Celsius. And what we see is that the temperature begins to go up. So here at this point on the graph, we have all solids, okay? Like the water is completely solid. So this is ice, which means the particles are really close together, but because the temperature is moving up, just as a reminder that temperature measures the average kinetic energy, or the amount, sorry, hold on, my little screen is in the way, the average kinetic energy, or basically the speed of the atoms. So if the temperature is increasing from -5 to 0, because the line is going up, that means that the molecules are moving faster. And this would be true for all of the angled portions. So here and here. They are all moving faster when the line is moving up. Now, at this point, at 0, there's a flat line. Now, the reason why it's flat is because here, the energy that's being applied, the heat that's being applied, is being used to do something different than just speeding up the molecules. What happens is when the molecules move so fast, eventually their speed is great enough to be able to break down or weaken their intermolecular forces. And so here, when those forces are broken or weakened, that's when you start to melt. So here the ice is beginning to melt, and notice the temperature does not change. So if we were at school, I would show you guys this by letting you melt ice on a hot plate. If you had a thermometer in there, it would stay at around 0 for a long time. It's very flat because the temperature, the molecules are not speeding up. All of the energy is going into weakening the intermolecular forces, holding all of those water molecules to each other. And then once it's completely melted here, okay, it will turn into a liquid. Okay, so we have a solid down here, and then we have melting happening, and then we have a liquid, and then once the liquid reaches 100 degrees, it's going to start to experience vaporization, which, remember, vaporization can be two different things. It could be boiling, or it could be evaporating. Things don't have to boil in order to evaporate and experience vaporization. And then once it's 100% vaporized, then it's all a gas, and the gas molecules will begin to heat up. And so you can see it kind of goes in order: solid, liquid, gas, and we see vaporization and melting as our two phase changes. Now, with a cooling curve, you're going to see something very similar, but instead of heating up, It is cooling down. So a cooling curve of water has those same important temperatures of 100 degrees Celsius and 0 degrees Celsius, because again, this point here, we call this temperature the boiling point, based off of the temperature where everything starts to boil or vaporize. And then 0 degrees Celsius is called its melting or freezing point. It's like called both. But we never call 100 degrees its condensation point. I mean, I guess you could, but it's not really that common to do so. So here we have the same temperatures, but if you're cooling down, that means the temperature is going to go down. So that means we start with a gas, and then as the gas reaches 100 degrees, the energy that's releasing is being used to reform the intermolecular forces. And so we see condensation start to happen. Now remember, condensation is like if you have a glass of ice water and the outside of your glass starts to feel wet. It's not that your glass is leaking water, it's that the water in the air around it is cooling down and becoming a liquid again. So condensation occurs and it turns into a liquid. And then once that liquid reaches 0 degrees, or the freezing point, it will start to freeze, and then it becomes a solid again, or ice, as we commonly call it. And so again, at these angled points here for the gas, the liquid, and the solid in a cooling curve, what that's going to mean is that the molecules are slowing down. There. That's what that's going to mean. And so these are kind of the cooling and heating curves. And from these, you can actually calculate the amount of energy that's released and things like that, which we'll go into. So just some like basic notes to make sure that you really understand like what I need you to know is that the flat lines or the plateaus on the graph are phase changes. So these are phase changes. And remember, a phase change is going, from solid to liquid, liquid to gas. And that means that the energy is being used to either speed up, not speed up, that's a different blank. They're being used to either break or form the intermolecular forces. Which intermolecular forces are often abbreviated as IMFs, intermolecular forces. And the slanted lines are heating or cooling. And so that means the energy is being used to either speed up or slow down the atoms or the molecules. And so remember that speeding up or slowing down is due to a change in the kinetic energy, okay? Which, remember, the average kinetic energy is measured by the temperature. And the reason why we see this happen in distinct stages is the energy can only be used for one process at a time. It can either speed up or it could break intermolecular forces. It can't do both at the same time. So the atoms are not going to be speeding up or slowing down at the same time that a phase change is occurring. And so what I would like you to do is I would like you to pause the video and answer these questions. So I want you to explain the difference between endo and exothermic. And I want you to tell me which curve shows an exothermic process and which curve shows an endothermic process. So pause the video and press play when you're ready to go over the answer. Okay, so endothermic, we know endothermic means that you absorb energy, right, or absorb the heat. And exothermic means that you are releasing the heat, which we often show as endo absorbing the heat as being a positive Q, and releasing the heat is a negative Q, right? And so when we think about which one is exothermic, if exothermic is releasing the heat, remember if an object is sending heat out into the surroundings, that means its temperature is going to start to decrease. So exothermic processes are ones that are cooling down. Like they themselves are cooling down because they're putting all of the heat into their surroundings. So this would be a cooling curve. And to explain why, because that's always important, we know that because the temperature is decreasing. And so an endothermic process, again, is absorbing heat, so its temperature should be increasing. So this means it is a heating curve. And again, it's because of that temperature increase. Now, heating and cooling curves do have some calculations. I'm going to show you them all at once, but I just want to be upfront with the fact that these calculations, I would only ever ask you to do one segment of the graph, not all segments together the way I'm going to show you. If we were in regular school and not digital online, I'd be asking you to, do a problem where you have to calculate all 5 together. But we're going to keep it simple for this digital learning. So if this is a heating curve, right, because we see that the curve is heating up, we want to label our x and y axis. So we know that our y-axis is going to be temperature measured in degrees Celsius. And we know that since it says it's for water, that means this segment has to be happening at 0 degrees Celsius, which I'm not sure I can fit. There we go, 0 degrees Celsius. This one is at 100 degrees Celsius, right? So those are where our segments, our flat lines are occurring. And our x-axis is either time in seconds, or it can also be energy in kilojoules. And so what I want to show you on the right side is they've given us several values here. And so these values are a couple different things. So we know that C is the specific heat capacity. And the specific heat capacity is different for H2O if it's a solid, liquid, or gas. So we have the specific heat of ice, the specific heat of water, and the specific heat of vapor, or H2O when it's a gas. We also see this delta H value here. And I want us to pause on this calculation, and we're going to go over to a little graph to kind of summarize our phase changes, and I want to explain what delta H is. Delta H means the change in enthalpy, which enthalpy is basically energy. So you're probably wondering, okay, well, why aren't we just using energy? Well, it's specific, meaning that it's a change in energy, but it includes the work plus the heat. So we know that when a compound heats up, the atoms start to expand, which is work, but it also has heat involved. So enthalpy is the total energy, work, and heat, whereas typically when we're talking about our change in temperature or things like that, we're specifically talking about just the energy related to heat. And so there is a certain amount of energy, both work and heat, required to break or form those intermolecular forces. So just as a review of our phase changes, when we go from a solid to a liquid, that is melting, and that is going to be a endothermic process. And so we call its enthalpy, or change in enthalpy, delta H of fusion. Which we saw on our graph was abbreviated as FUS. So delta H of fusion, and delta H of fusion is used for both melting and freezing, but for melting, our delta H of fusion is positive because it is endothermic. Now, the reverse of melting, going from a liquid to a solid, is freezing. And this is going to be an exothermic process, which means it still requires the same amount of energy, or delta of enthalpy, delta H, but it's being released, so it's negative. And so when we change from a liquid to a gas, that is vaporization, which again can be boiling or evaporation, which is going to be an endothermic process. You cannot boil water if you're not putting heat into it. And so we call this enthalpy delta H of vaporization, which we abbreviate as vape. So delta H of vape is vaporization, and because it's endothermic, that means this is the amount of energy and work that is positive, it's absorbed. And going from a gas to a liquid, the reverse of vaporization is condensation, and that is an exothermic process. And again, it's delta H of vape, but it's a negative value. Now, oftentimes they're only reported with a positive number, and if you're doing a cooling curve and not a heating curve, you have to remember to change it to a negative on your own. Now, a solid to gas, this is sublimation, and we're not going to really talk about it a whole lot, although, again, if we were in class, I have a dry ice lab, and we would really get to do it. If you want to look something up online just to see what it would be, look up the triple point of CO2, and you would see the lab that we would have done in class with dry ice. But sublimation is an endothermic process. It means it's going straight from solid to gas. It's skipping the liquid phase. And so we call this delta H of sublimation, and it's positive because it's endothermic. And then we have deposition, which has the word deposit in it because the gas goes straight to a solid and it looks like something is just deposited or left there. And that's exothermic. And again, delta H of sublimation would just be negative for deposition. And so, yeah, I just wanted to take a moment to explain what delta H was and kind of summarize our phase changes for us. So if we go back to our graph, we see all of those there. And so at each segment, you use a different formula because when there are two formulas that we use, the one that we're already really familiar with, M times C times delta T, but this only works when there's a change of temperature. So that formula can be used in a couple places. You can use Q equals M times C times delta T there. All the slanted spots can use this formula because there's a change in temperature. But during a phase change, there's no change in temperature. So then you have, so this one is used for phase changes. And, oh, sorry, not for phase changes. This is for heating or cooling. This is heating or cooling. But for a phase change, you use Q equals your mass times your delta H. So, for example, for the melting portion, you would use Q equals M times delta H of fusion, right? Because that's what it is when it's melting. And for the vaporization, you would use Q equals M times delta H of vaporization. Now, the one thing you want to remember is that for your Q equals MCAT, your C for each of those is different for ice, water, and vapor. And so what you can do is you can actually calculate how much energy it would take to take water all the way from -5 degrees Celsius all the way to 120 degrees Celsius, or really whatever temperature you wanted. You could actually calculate the energy required for that using these values. And so I'm going to show you how to do that. And what you do is you break the section, like solve for each of these segments, and then you add them all together. So if this first slanted section is Q1, right? And then this one is Q2 and Q3, and then Q4, and Q5, then all of the energy together, so Q total, would be equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. So you just solve 5 different formulas and then you just add them all together. So if we wanted to do this, so this sample problem here, you would take, we've got the mass of our ice, and they want us to go from -5 to 120 degrees Celsius. So we would do segment number 1. So Q1 is equal to the mass times the specific heat of our ice, because we know it's a solid at that point, times our change in temperature, which our delta T for this segment would be our T final minus T initial, which is 0 degrees minus a -5 degrees Celsius. And when you subtract a negative, it turns positive. So our delta T is 5 degrees. And so what we do is we just plug it in. We say, okay, Q1 is equal to 100.0 grams times the specific heat of ice, which if you look at what is up here is 2.10 joules per grams degree Celsius times 5 degrees. And when you multiply that all together, you get 1,050 joules of energy. So that is how much energy it takes for segment number 1. And so then we would do segment number 2. Segment number 2 is heat, the melting portion, right? This is where things are melting. So that would be Q2 is equal to M times delta H of fusion. And so that would be 100 grams times, if you look for our delta H of fusion, that's 334 joules per gram, which means that Q2 is equal to 33,400 joules. So we have our answer for segment 2. And then we have segment 3, which is when our liquid is heating up. And what we can do is we can look at our graph to see our temperature change. That segment starts at 0 degrees Celsius and ends at 100 degrees Celsius. So that means our delta T is 100 degrees Celsius because it increases by that much. So then Q3 would be equal to M times C of water times our delta T. So Q3 is equal to, well, we'll plug it in over here, 100.0 grams times 4.184 joules per grams degree Celsius times 100 degrees Celsius, because that was our change in temperature, which will give us 41,840 joules. So we have segment 3. And even though this is quite tedious, it's not complicated to do this math. Segment D is when the liquid water is vaporizing and there's no change in temperature. So our formula for Q4 is just M times delta H of vaporization, which is 100 grams of H2O times 2,260 joules per gram. And remember, we're getting our delta H of vaporization, like they're right here on our graph. We're not memorizing these numbers. You will be given them in a problem if you need it. And so when we multiply all of this, Q4 is equal to 226,000 joules. So that's our answer for Q4. And then our last segment is when the gas is heating up. And so that means Q5 is equal to Q5 is equal to M times C of our vapor times delta T, which our change in temperature, they mentioned that the highest they want us to go to is 120. So that means we're going from 120 degrees Celsius to, well, we're starting with 100 degrees and then increasing to 120. So that gives us a delta T of 20 degrees Celsius. So that means Q5 is equal to 100 grams times our specific heat of our vapor, which is 1.90 joules per grams degrees Celsius, times our delta T, which is 20 degrees Celsius, which means that Q5 is equal to 306,090 joules of energy. And so to get your total, you would literally add all of those highlighted yellow numbers together, and you get your total energy required to do the whole process, which is actually quite a bit of energy. One thing that I would like to draw your attention to before we end this video is one thing you might have noticed is that the amount of energy required to vaporize is a lot bigger than the amount of energy required to melt. And the reason why is when you're melting, the intermolecular forces are weakened here, but when it becomes a gas, the intermolecular forces are completely broken. And so it takes a lot more energy to completely break them than to just weaken or loosen them, which is why it takes a lot more energy. And you'll see that here as well in the heating and cooling curves I drew. So this was a longer video, I'm sorry, but we are all done. So have a good weekend, guys.